Welcome back. We can see that our learning objectives for this video are to classify matter either based on phases or based on composition. We're going to discuss the properties of matter in this chapter. But first, we should clarify and identify what matter is. So, what is matter? Matter is the stuff that makes up the universe. So basically just everything. It's everything in the universe that has some mass and some volume. There are some examples on this slide, but basically it's just everything that exists occupying space in the universe. The alternative to matter in the universe is energy, which, okay, more on that coming soon in some future videos. Okay, so everything in the world is made up of matter. Now we want to understand how matter behaves the way it does and why it behaves that way. So we need to zoom in as far as possible and think about what matter is made out of. The answer is atoms. Everything is made out of atoms because these are the building blocks of our elements, the building blocks of matter. Atoms are just like building blocks. Think about maybe like Lego pieces. You can fuse them together to build up to more complicated structures that we call molecules. Now, zooming in here is incredibly hard to do physically because these atoms are so incredibly small. Most of the pictures that we'll have and that we'll look at in this course are going to be drawings or animations or cartoons, but there are a few techniques that can actually visualize atoms, one of which is showed on the right-hand side of this slide. Here we have a strand of DNA laying on a flat surface, imaged using scanning tunneling microscopy, which is a scanning probe technique to look at individual atoms and molecules. All right, showing that it is possible to look at these atoms, but unfortunately it's extremely difficult. So instead we'll look at more of these kind of cartoon pictures and build up our fundamental understanding from them. We said our goal is to classify matter into different categories, maybe group them into different buckets based on some similarities. The first way that we're going to do this is by grouping matter based on their phases. There are 3 common phases and a few uncommon phases, but we'll focus on the 3 common ones here, which are solids, liquids, and gases. In our lives, we have certainly experienced solid materials, liquid materials, and gaseous materials. But we're going to take a moment and try to zoom in to that atomic level picture to get a better understanding of why our solids and liquids and gases behave the way that we know that they should. We'll start by talking about solids. Solids have our atoms packed together as tightly and densely as possible, and at the same time, those atoms are held together rigidly. In our diagrams, we can see our atoms, represented as these little spheres, packed together, touching all the other spheres. They are stuck there in place next to those other atoms. Because our atoms are packed together as tightly as possible, our solids are going to have a fixed volume. You can't make them any smaller because they're already touching each other. And you're not going to make them much bigger because then it wouldn't be a solid anymore. We need to have those atoms touching against each other, held together rigidly. Our solids also are going to have fixed shapes, again, because of that rigid structure. And lastly on this list, our solids are incompressible. We can't smush them together, compress their volume to be any smaller, because once again, those atoms are as packed together as possible already. We have two distinct pictures of our solids. Actually, we can classify these one step further. The solid on the left with our small purple atoms and our large green atoms is called a crystalline solid. Crystalline solids have long-range repeating patterns. There's going to be, in this case, a pattern of green, purple, green, purple, green, purple that can repeat forever and ever and ever as long as we want. We can look at that pattern and predict exactly where the next green atom should be, where the next purple atom should be, so on and so forth. The alternative are called amorphous solids. Amorphous solids do not have a repeating pattern. All those atoms are just jumbled together, still packed together and held rigidly, but you can't predict where the next one is going to be because there's no repeating pattern to base that off of. One last note here about solids before we move on. Oftentimes we like to abbreviate and write things down efficiently. We can represent solids by writing parentheses S. And this is a common abbreviation for us chemists. Moving on to liquids. Liquids we can likewise abbreviate. Here we can go parentheses L. I like to draw a cursive L, so it does not look like the number 1, but we can draw parentheses L to represent liquids. And once again, let's start to think about our atoms to gain a better intuition about why liquids behave as we know that liquids have to. Our liquids still have those atoms packed together as tightly as possible, but now they're not held together rigidly with the neighboring atoms. Instead, these liquid atoms are able to move and flow past each other. One way to visualize this in your head is to think about the balls in a ball pit that you might have gone to as like a little toddler. These balls are all touching each other, they're close together, but they're able to push around past each other and move around freely if there's some energy applied to them. If we think about our atoms in this way, we can still think about our liquids as having fixed volumes, because that's dictated by how close our atoms are to each other. Once again, they're stuck touching each other, so they have that fixed volume. You can't get any smaller. But since our atoms are able to move around past each other, our liquids now have indefinite shapes. They will flow until they take on the shape of their container because those atoms can move. They're not stuck to each other. Lastly, we'll talk about gases for a moment. Gases we like to abbreviate parentheses G. And in our gases, if we're thinking about our atomic structure, gases are no longer touching each other. We have a phase of matter that is no longer condensed. In fact, there is large distances between our gas atoms. In our gases, in fact, most of this gas is composed of empty space, and there are just these tiny little atoms that are separate from each other, ignoring each other, bouncing around the world. One way you can picture this is like the animation on the bottom right side of this screen. If you've ever seen a DVD screensaver or a computer screensaver, our gas atoms bounce around their container, just like on this screensaver. Well, ignore that restarting of the animation. But our gas particles bounce around until they hit the container. Then they can bounce off of it and continue on their way. The result of this behavior is that our gases now have indefinite volumes and indefinite shapes. We can change the volume, we can compress our gases because there's a lot of empty space. We can change the size of the box that our gas atoms are bouncing around in, and that's fine. They'll just bounce around in a smaller thing. It doesn't matter. There is empty space that we could get rid of. Likewise, we can change the shape of their container, and the same thing will happen. Here we have a quick summary of our 3 common phases of matter: solids, liquids, and gases. Our second goal was to categorize matter based on composition. As it turns out, matter comes in a variety of different forms, depending on how it's prepared, purified, found, etc. The 2 major categories in this system are pure substances and mixtures. Pure substances are generally hard to find or hard to prepare, but they're composed of only a single thing. We have only one atom there, or we have only one molecule there. We've gotten rid of any impurities, and we have only a single pure substance. This is hard to do, and in fact, most of the matter that you encounter in your everyday life is going to be a mixture. Mixtures are composed of multiple different substances combined together. Maybe you have 2 different atoms mixed together or multiple different molecules mixed together. And what is sometimes nice about our mixtures is that we can change the proportions, the ratios of that mixture to suit whatever need that we have. Our picture on the right shows some salt water. Salt water is a mixture. Here's some salt water from the ocean, where we have maybe a fair amount of salt mixed into our water. This mixture of salt water found in the ocean could be different than the salt water that you use to cook pasta. We can change the amount of salt that we put in the water because it is a mixture. We can change the concentration. In this classification system, we can actually go a step further. If we're thinking about our pure substances, just a single type of substance, pure substances can be either simply elements or they can be compounds. Elements are the building blocks of our world. They're listed out on the periodic table of elements, which you have probably seen in our lab room or in various science classrooms that you've been in. And there's only about 118 elements that humans have found or made. These elements can't be broken down into simpler substances. They are kind of the fundamental building blocks, the fundamental atoms of our universe. Alternatively, we said before that we can use our atoms to build more complex structures known as compounds. Compounds are 2 or more elements fused together, chemically bonded together in a fixed and definite ratio to form various substances. On the right, we have water. Water is known as the formula H2O because it's made of exactly 2 hydrogens and 1 oxygen in each of our water molecules. This is subtly different than our mixtures. Our compounds have to have a very defined ratio of their atoms, of their components, chemically bonded together in that ratio to be that compound. We said salt water from the ocean and salt water from your cooking pot might be different concentrations because it's a mixture. Water is never going to have different ratios in its composition. It is always going to be exactly 2 hydrogens bonded to 1 oxygen because it is a compound. Switching back to our mixtures, we can again go a step further and classify our mixtures in 2 different ways. The first type of mixture is known as heterogeneous mixtures. In our heterogeneous mixtures, our composition is not uniformly mixed. We can visually distinguish between the different components of that mixture. As in, we can look at the mixture and see where one component is and where a different component is. Or another way to phrase this is that if you grab a sample of this heterogeneous mixture, it might be different than the next sample of that heterogeneous mixture that you grab. Our example is on the left here. It's this giant ice cream sandwich. Well, perfect sized ice cream sandwich, which is composed of all sorts of things. This cookie, the chocolate chips, the ice cream, all of which are, also composed of different things: sugar, flour, butter, cream, etc., etc. But this is definitely a heterogeneous mixture. I can see where the chocolate chips are and where the ice cream is. One sample I take and put into my mouth might taste different than the next sample I take and put into my mouth. Maybe one bite is mostly cookie, the next bite is mostly ice cream. The second type of mixture is a homogeneous mixture or homogeneous mixture. In these types of mixture, our composition is exactly the same throughout the whole thing. It is uniform. Or another way to say this is that we cannot look at this and see where one component is versus the other components. Or yet another way to phrase this, we can take multiple samples and all of those samples should be the same. This is still a mixture and it might be different than another person's mixture where they change the concentration. But within a mixture, at least this concentration should be uniform. Our homogeneous mixture here is this regular sized cup of coffee that someone might drink in the morning to get going. Coffee is composed of water, some caffeine, some different flavoring compounds, all that different stuff from the coffee beans that we extract. Can you look at that cup of coffee and see where the water is and where the caffeine is? Well, no, you can't. It's all mixed together uniformly. Or depending on how you like your coffee, maybe you put a little bit of sugar in that coffee as well. It will dissolve nicely. Mix in some milk or cream, that will dissolve nicely. You can't look at that liquid and see where one component is and the other component is. Or if we take 2 different sips, both of those sips should have exactly the same composition. We're not going to have 1 sip of all water, 1 sip of all sugar, 1 sip of all milk, whatever. Every sample should be the same. Okay, here is our summary for separating matter based on its composition. Pure substances or mixtures, And then our pure substances can be either elements or compounds. Elements appear on the periodic table. Compounds are multiple elements combined together in some definite ratio. Our mixtures can be homogeneous if they are mixed uniformly, or heterogeneous if they are not mixed uniformly. All right, let's put our knowledge to the test. I'll talk through the last 3 of these examples on this slide, but I'll leave the first 4 as practice. If we're talking about a lead weight, well, our first system, we would call this a solid. But in our second system, we would need to classify this as either a pure substance or a mixture. A lead weight, lead is just one thing. So in our second system, we will call this a pure substance. And we can ask ourselves, is lead on the periodic table of elements, or is it some combination of those elements? Here, it is on the periodic table. This is a pure element. Its symbol Pb on that periodic table. Second, we can think about seawater. Seawater is going to be a liquid, but if we're answering the question here, our second category system, seawater has multiple components. It is not just a single thing. So seawater has to be a mixture. And if we want to go one step further, we can ask ourselves, can we see the different components of seawater with our eyes? A few ways of thinking about this. If you're going to define seawater as just salt water, water and salt, those mix together nicely, and I would say that is homogeneous. Although if you wanted to say that your seawater contains little bits of seaweed and maybe a fish swimming around, that could technically be called heterogeneous. So either way could be okay, but you would want to defend your answer maybe with some logic. Our last example is distilled water. Once again, this is a liquid. But to answer the question on this slide, distilled water, well, this word distilled means that it has been purified. So our distilled water is a pure substance. The next question, can we find water on the periodic table, or is it made up of multiple things on the periodic table? Well, we mentioned this on the previous slide. Water is H2O. Well, hydrogen is on the periodic table, oxygen is on the periodic table, but water is a combination of those two things. So our water has to be a pure compound. There we go. We've gone through at least a couple of examples. We have 4 more for you to do. Try to pause the video, find some paper, and write down some answers. There we have it. I hope we've accomplished our objectives here, being able to classify matter based on different phases or based on composition. Well, there we go. Thanks so much for tuning in. Hope you all have a great day, and I will catch you next time.